Okay, in this section, we're going to be looking at asymptotes. Okay, if you look at letter H, you can see limits at infinity. The way we find a horizontal asymptote for any function is you just look at the limit as x goes to infinity, or you look at the limit as x goes to negative infinity. And if it's equal to a number, then you can say, well, that's the horizontal asymptote. Y equals that number. So if you look at the tangent inverse example, this dotted line right here and this dotted line right here are the two asymptotes. So the limit as x goes to positive infinity is going to equal pi halves, and the limit as x goes to negative infinity is going to be negative pi halves. So you're getting an actual number. In this case, we actually have two horizontal asymptotes. If a function has a horizontal asymptote, it usually has only one. Okay, but it's important to note that if you're looking for a horizontal asymptote, you have to look at the limit as x goes to infinity. That means what is happening on the right side as x goes to infinity. Is it approaching a certain value? But you also have to look at the limit as x goes to negative infinity of that function. So what's happening on the left side, because sometimes you get a different answer. Okay, now we're going to look at horizontal asymptotes for rational functions. Here it says pay attention to the biggest power to determine if it has a horizontal asymptote or not. In the first example, the biggest power is the same. So when your biggest power is the same, you just take the coefficients. So in this case, it'd be 2 over 7. Y equals 2 over 7 is just a horizontal line, and that would be your horizontal asymptote. In our second example, the power on the bottom is bigger than the power on the top. Again, you're just looking at the biggest piece, ignoring everything else. In that situation, it's going to be y equals 0. Your horizontal asymptote will be y equals 0, which is just the x-axis. In our third example, the degree on the top is bigger than the degree on the bottom, and in that situation, there is no horizontal asymptote. Now, there is a special case that we look at, and that's when the degree on top is exactly 1 bigger than the degree on the bottom. In that situation, we get what's called a slant asymptote. A slant asymptote is not a horizontal line, it's a line that's diagonal. And to figure out what the equation of that line would be, you would have to do long division. When you do long division, you're going to get something like this, a number times x plus a number, and then you're going to have a remainder, and you want to just ignore the remainder. Okay, let's go through some examples. The first example is the bottom is bigger. Again, you want to ignore the smaller stuff, crossing this out, and just pay attention to the biggest degree. The highest power on the top, the highest power on the bottom. So you get x squared on top and x to the third on the bottom. Because the bottom is bigger, it's just automatically y equals 0. Okay, if you did the limit as x goes to infinity, you would get 1 over infinity, and that's the same as 0. So y equals 0 is your horizontal asymptote. For the second example, again, you're ignoring the smaller degrees. The biggest power on top is x squared, the biggest power on the bottom is x squared. That's the same. Anytime you have the same, you just take the leading coefficients. The top was a 6, the bottom was a 2. 6 over 2, well, that just gives you 3. So y equals 3 is your horizontal asymptote. Okay, in our last example, the degree on the top is 3, the degree on the bottom is 2, so we would have no horizontal asymptote. Some of you might notice that the degree on the top is exactly 1 bigger than the degree on the bottom, which means that we would have a slant asymptote. But we're not going to do anything with slant asymptotes right now, so we're just going to say no horizontal asymptote. Okay, this is an example that we already looked at, tangent inverse. The reason why we're taking another look at it is just for me to point out the fact that if you're doing a horizontal asymptote, you have to look at the limit as x goes to infinity, and you have to look at the limit as x goes to negative infinity. Most of the time, it's the same thing, but sometimes you end up with a different asymptote on each side. This is one example. You have the limit as x goes to infinity for tangent inverse is going to be equal to pi over 2. So as x goes really, really far to the right, it's approaching y equals pi over 2. Now the limit as x goes to negative infinity for this function is actually approaching a different asymptote, is approaching negative pi halves. So the only reason I'm showing this example again is just to point out the fact that if you're doing a horizontal asymptote, you really should be looking at the limit as x goes to infinity, and you should also be looking at the limit as x goes to negative infinity. And if it's equal to a number, then you end up with a horizontal asymptote, and it's just going to equal that number. Okay, if you look on the right, you can see this y equals, and then there's a rational function there. And what I've done is I've kind of factored it so that you can kind of see what's happening. We do have an x plus 3 over x plus 3. So what that means is we can kind of cancel that, but it means that we have a hole when x is equal to negative 3. You can see the hole in the graph. If you were to graph that on Desmos or something, the hole would not show up. So now, after ignoring the hole, you can see we're left with x minus 2 over x plus 1. And now we're going to try to pay attention to the asymptotes. For a vertical asymptote, you want to look at what's happening after you cancel. You can see x equals negative 1 is going to be a vertical asymptote. But just looking at the graph, you can see that the limit as x goes to negative 1, you get a different answer from the left as you do from the right. One of them is positive infinity, the other one's negative infinity. But regardless, if you get an infinity or a negative infinity or any of those kind of things, we're going to say that there's going to be a vertical asymptote at that spot. Okay, the second thing we're going to look at is the limit as x goes to infinity or negative infinity. We said that together, those limits will tell us if there's a horizontal asymptote or not. You'll notice that they both have the exact same power. If you look at the biggest degree on the top and the bottom is 1. So what that means is we can go ahead and take the coefficients of those because they're the same power. X to the 1 on top and x to the 1 on the bottom are the same power. So we can just take the leading coefficients and 1 is the answer. So y equals 1 is our horizontal asymptote. Notice that both of our limits were equal to 1. So we just have one horizontal asymptote, and that would be y equals 1. Okay, now we're going to look at some more examples for horizontal asymptotes. Again, you're looking at the biggest degree on top and the biggest degree on the bottom, but it might not be in order. Be careful. They might try to trick you by putting it in the middle or towards the end. So you want to look for the highest degree and then ignore everything else. So in this first example, I'm going to ignore the 5. I'm going to ignore the minus 7x. It's very important to note that that minus belongs to the 8x squared. On the bottom, 2x squared was the biggest piece. So we're just going to look at this. So that top limit, because we're going to infinity, is similar to that bottom limit. Now you'll notice that they're both x squared, so we're just going to take the leading coefficients. And so that limit will just equal negative 8 over 2, which is negative 4. For the second one, we're going to ignore the 5. So the limit as x goes to infinity of all that stuff is similar to this limit here. So we can ignore the plus 5. And you'll notice they're both just the square root of x. That's the same power of x. It's a power of 1/2. So again, you're going to take the leading coefficients, 6 over 2. And 6 over 2, which is a 3, is going to be your answer to that limit. Now on the right side, we have something a little bit trickier. When you do the square root of x squared, the answer to that has to be positive. The square root of x squared is basically like an x. Except that you have to be careful because, again, it always has to be positive. You can't have that piece be negative. So on our answer, when we say similar to, we're going to put absolute values around that x. We can't just leave it as x. We have to put the absolute value around it to make sure that that piece is always positive. So now when I do this limit and I plug in my infinity, I'm still going to take the coefficients, so negative 16 over 2, so that's negative 8. And we have to be careful because we have to count our negatives, make sure we have the correct number of negatives. When I plug in a positive infinity, it doesn't give me any extra negatives, so I'm okay. But you'll see on the next example, we might get an extra negative. Let's look. Because we're doing the limit as x goes to negative infinity, now it's basically the same problem, so it reduces to the same thing. But now, because we're plugging a negative infinity in, we will get an extra negative on the top. So we're going to have negative 16. And I'm going to put negative 1, even though it's negative infinity. The bottom does not get an extra negative because the absolute value, it does not get an extra negative. So we got to count our negatives here. We have 2 negatives that cancel. So this one gives you a positive 8. So the square root of x squared has to be positive. And when you plug a negative infinity in, you got to be careful about the negative part of it because it does give you an extra negative on top because that piece on top is allowed to be negative. It does not give you an extra negative on the bottom because you're taking the absolute value of that negative infinity. And so that negative is disappearing on the bottom. So that's a tricky example that you have to be careful about. Okay, nothing new here. We're just going to do some examples. Doing that first limit as x goes to infinity. The biggest piece is negative 8x to the third. And the bottom, the biggest piece is 2x squared. We do notice that the top is bigger, so our answer is going to be infinity. But we do have to be careful. We've got to count the negatives to see if we end up getting positive or negative infinity. When you plug the infinity in, you don't get any extra negatives. However, there is a negative right here in front of the 8. So we do have one negative, so we'll say negative infinity is our final answer for that one. Now we're going to do the exact same problem, But this time we're going to go to negative infinity. So again, we still have a bigger degree on the top, so we're still going to get an infinity for our answer. But now we do have to be a whole lot more careful about how many negatives we have. We're plugging a negative infinity in, so that's going to give us 3 extra negatives on top and 2 extra negatives on the bottom. So that's 5 extra negatives, and you include the original negative that you have, so that's 6 negatives. 6 negatives, they're all going to cancel, and you're going to end up with positive for your answer. So for the second one, we're getting positive infinity for our answer. Okay, here's kind of a weird function. Square root of x squared minus 3. The graph is over here, it goes to the right, it goes to the left. I'll put some arrows on it. Okay, when we're doing the limit as x goes to infinity, we're going to ignore the small stuff, so ignore the minus 3. So we kind of just have the square root of x squared. And we talked about how that always has to be positive. So the way to make it positive is put the absolute value around it. So the square root of x squared is going to be similar to absolute value of x. So how do you do the limit as x goes to infinity of the absolute value of x? Well, you just plug in the infinity and you get infinity. What if we were doing the limit as x goes to negative infinity? Would that be any different? Well, this is still similar to the same thing. It's just we're going to plug in a negative infinity instead of an infinity. But the absolute value is going to get rid of that negative, so you're still going to get infinity for your answer. The special note on this problem is that the square root of x squared is not the same thing as just an x. Okay, here's just some more examples. We want to look at the biggest piece. Biggest piece on top is minus 8x squared. Biggest piece on the bottom is square root of 16x to the fourth. Square root of 16 is just 4. Square root of x to the fourth is just x squared. You don't need absolute value because it's already positive. X squared will only be positive. Okay, you probably noticed they're both x squared, so you can just take the coefficients. Your answer will be negative 8 over 4, which is just negative 2. Okay, on the other side we have a similar example. Biggest thing on top is minus 6x to the third. Biggest thing on the bottom is square root of 9x to the 6th. Square root of 9 is 3. The square root of x to the 6th is kind of like x to the 6th to the power of 1/2. Now in this situation, you do get x to the third, but you're only allowed to do this assuming that you get positive answers for your x. Now we can actually plug negatives in if we leave it like this, so we have to fix this by putting absolute value around it. Another way to think about it is that this entire bottom piece has to be positive. It's a square root of something. You can only get positive because that's a function. It's a square root function. So we can't change it into something like this that allows negatives. We have to make sure that it's similar to something that's also positive. So by putting the absolute value around it, it stays positive. Okay, let's go ahead and do the limit. We're doing the limit as x goes to infinity, so we're not plugging any negatives in. So your answer is just going to be the leading coefficients since they're both powers of 3. Final answer to this one is negative 6 over 3, which is negative 2. Okay, again, focusing on asymptotes, we want to ignore the part that's going to be a whole. X minus 3 over x minus 3 would be a whole at x equals 3, so we're going to ignore that. Vertical asymptote is really just whatever makes the bottom 0 after you cancel all the wholes. X equals 5 would give you 0 on the bottom, so x equals 5 is an equation of your vertical asymptote. Now if you multiply everything out, you can see over here, we have x squared on the top, x squared on the bottom. That's the same power. So for your horizontal asymptote, you would just take the leading coefficients. Leading coefficient on the top is 1. Leading coefficient on the bottom is 1. So y equals 1 over 1 is your horizontal asymptote. And that's it. Okay, this is our last example. This is an example of a real AP test question. If they give you the information at the top that says x is equal to 9 is a vertical asymptote, and y is equal to 3 is a horizontal asymptote, then which function below would be the correct function that has these properties? First thing we want to do is ignore the wholes. Now in order to get a vertical asymptote at x equals 9, I would need to have x minus 9 on the bottom. B does not have an x minus 9, and neither does D. The next thing I would have to happen is when I multiply everything out, the x values need to have the same power on the top and the same power on the bottom, and the leading coefficients need to be 3 over 1. For C, the leading coefficients are 1 over 1, so that's no good. But for A, the leading coefficients are 3 over 1, so the answer would have to be A.